Hello friends, welcome back to the Dr. Tristos channel. I'm your host, Dr. Tristos, and we're going to continue with our example demo program today, and we're going to do a couple of things. We're going to try to make this code a little more readable and perhaps add an additional function to it. So the boss came over and said, you know, this code you're writing is great, but we have to be able to maintain it in the future, and we need it to be more readable and easy to understand. In the last video, I talked about how we can use blank lines in the Zilog development system to kind of group or separate our code based on the function. So here we can see when I'm setting up my initials register values, I group those in one group. When I'm testing the UART to see if it's ready, I'm grouped into another group. And outputting a character is yet another group. And deciding if we need to loop again, and then what to do if we do not need to loop and output more characters, yet is in another group. To me, this makes it more readable. On most assemblers I worked with, you cannot have a blank line, but you'd have to have a semicolon. And that's fine, you know, you can do that. I guess I'm just strange, and I think it looks better when I can just have blank lines. So, one of the things that about being readable and maintainable in the future, I see you were doing a test ready, get status of transmitter, okay, and we're doing an in instruction on a memory location, on an IO location Charlie 5. Then testing bit 5. Okay, so I can go from the notes, transmitter holder empty register, holding register empty. I can guess that this must be a status register. But wouldn't it be a lot clearer if we could use a name here for the register? So then I could look and say, I know which register that they're inputting there. And then you have a general idea of what the programmer was trying to accomplish. So it just so happens that I have an equate statement up here we have not used yet. It's before the org, which is fine. The equate could actually appear anywhere in the code. And this is the line status register, Charlie 5. See if I can copy that. So here's our line status register, which is equated to Charlie 5. So that means that anytime the assembler runs across the string of characters that spells UART1 underscore LSR, anytime that it runs across that, it's simply going to replace that string of characters with Charlie 5. Okay, so here where we're using the physical address, we're now going to put in our equate UART1 LSR, line status register. So now when the assembler sees this, it'll assemble as input to register A, Charlie 5. IO address Charlie 5. So now when you're trying to maintain this code in the future, makes it a lot easier there. I look down and say, oh, that's where he's checking the line status register. Again, these abbreviations are not mine. Like for instance, LSR is not mine. However, this is Zilog's abbreviations that they use. So we have another IO down there at Charlie 0, And you know what that is? That's the UART1 THR. Okay, so okay. So we got a little bug here. This would actually run and work. I don't know if anyone else has picked up on this yet, but I called it UART1. So this would run and work because although we're using that term UART1, we gave it the values of UART0. It's physical Charlie 5, Charlie 0 is UART0. So I really need to change these labels here. My apologies, but it's also a good example of where if you use the wrong names, this would assemble and run if it was all if it was laid out correctly, it would run. It would run with the wrong names, etc. But the most importantly, it's going to assemble with no errors. So if you didn't have any UART output, perhaps you used the wrong label and was sending it out UART1. Your code's going to assemble just fine. You have a typographical error calling it 01 instead of 0, so you're going to be sending data to the wrong port. Here I had a double error. I was using the wrong label and in two different places. So we have that corrected now. Okay, we don't need this part. So, as I told you, we orged this code at 3000 hex, which is a standard starting address for Tristos if he was writing assembler programs or some type of application. And, you know, that's something else we could do up here. We could, in our equates, we could call this example demo equate that to 3000 hex. So since it's starting with a numeric number, I don't have to put a preceding 0. So then if I come down here, I can't have two labels. It's called example demo. Let's do this. So now we're going to org at example demo. We're going to originate our program, and as we can see, example demo up here has already been equated to 3000 hexadecimal. So here the assembler is simply going to interpret the org statement, then here replace this text, example.demo, it's going to replace that with 3000 hex. So that'll get us going. Our first statement is jump to the beginning of the app, and here's the beginning of the app, and this makes it a little more readable. We now know the names of the registers that they're testing, and we have them in a name form, mnemonic form, which makes it a lot clearer to us. We have one place here. If the boss comes in and decides that one of my coworkers is going to load at 3000, I need to load at 4000, I only need to change example demo, the equate statement, I only need to change in one place. The program will then originate in the new location that we change it to. So anytime someone would say call example demo, well, guess what? It's going to example demo will have that value of 3000, and this is where the program is going to reside. So that looks a lot better. Looks a lot better to me anyway. So we're going to assemble this now. If we look down here at the bottom, we have 0 warnings, 0 errors. That's great. Let's do a build and go. Oop. I'm going to build it here. Download and go. There's no place to, there's no hardware attached, so it's not really going to download. It's going to run in the simulator, because remember in our settings we have this set to run in the simulator. Here's the output of UART1 or UART0. I'm sorry. We could switch between UART0 or UART1. I'm not sure if we can display them both at the same time. We'll play with that here in the future. But here's our hello world. Yeah, the boss is really happy with this, but he says, can you do anything else to make it more readable and so people can maintain it easier in the future and expand? And, you know, he said, you're taking up a lot of time writing code. You know, it looks like you write the same code over and over. You know, I started thinking about it, and, you know, he's right. We write a lot of code down here. Seems like we're always testing the UART to see if it's ready to send a byte out or not. So maybe I should, Python and these other languages, they have ways of creating functions that operate on operators, etc. Can I do that with assembler? Well, yes. There's limitations. There's things that it can do, things it can't do, but let's explore some of that. Let's go ahead and this test ready. Since I said we do this a lot of times, and we do it not only in writing code here on this project, but we need to use it on other code we're going to write in the future. So I'll tell you what, let's take that routine, because it's going to be the same in every program. Okay, it's going to always be the same. So let's put that up here, and now we'll start thinking about we're going to build a macro, and these are called macros, and will let us build our own functions. And this is similar to the EQUATE in that I told you anytime that the assembler sees UART0_THR, it's simply going to replace that with Charlie 0 hex. This % preceding Charlie's, it's another way of identifying this is a hexadecimal. This works in the ZDS system. Pretty universal. Putting an H afterwards of a numeric number works on pretty much all assemblers. Will tell it it's a hexadecimal number. So test ready, that's fine. But we have two UARTs, so maybe I better call it test ready 0, because we'll have to build one called test ready 1. And the way this works is our first statement says macro, to tell the assembler that what's coming is a macro. This test ready 0 is a macro. Now, we are inside the macro, and where we use UART0 LSR that's equated down here, that's still going to work just fine inside the macro. In fact, to answer your question now, in case you want to ask it, macros can be embedded. I'm not sure what level of embeddedness you can go, but a macro can call another macro, I'm not sure how far you can go with that, but I've found that this assembler is pretty well written to handle a large number of labels and etc. In the old days when you was programming on a Z80, I mean, you had to, I can remember having to limit your comments out here to the right. You know, normally this never makes up any assembler code, but simply that you were trying to save space on the disk, or your compiler could only, your assembler could only handle the comments, could cause it to overrun. It just had too much data. The comments are normally disposed of, but the files would just become too large. So you'd find yourself limiting the comments or abbreviating to keep down the number of bytes of the total source file. simply because the Z80 reached limitations there. Especially the linker. When you're using lots of symbols, lots of pointers, the linker has to maintain tables of all these symbols. And it can become a little much for a standard 8-bit processor. That's why we have this is Windows 64 here running an application that's writing code for the Z80, so I can create quite complex projects that when it gets all this compiled and assembled down and linked and just to a load file, it's something the Z80 can understand. So again, I'm sorry, but back to our macro. We need to end this. We need to tell the assembler where the macro ends. And in the Zilog development system here, we do that with a statement called in macro, and the label that we're ending, where it started. This is the label starting, and this is the end. Okay. So anytime we do this macro, it's going to wait in this macro, just like it did down here. It's going to wait inside running the code. When it assembles this, it will do exactly what it was doing before. And it's just that it's going to look a little cleaner now. So now down here in our source code, I'm going to test ready on UART0. Now when the assembler runs across this, again, it's simply going to go up here and get this code and fill it in here. But to me, looking at the program, I really don't need to see the macro. If I'm looking at the code here in the future, test ready 0, well, we've seen it a million times. In the other code, we know that he's testing the transmitter. In fact, test ready is not really a good name for that. Let's call it test transmit. If the transmitter is ready, because we could have testing the receiver to see if there's a received character ready. So let's change this. Okay. Let's see our one more place here. So now we're telling it to test transmit is ready on 0. Anytime I type this statement and it assembles, it'll fill in this code. Same thing we had before. That's much more readable than seeing a block of code and each time having to determine, what was this? Oh, that's right, they're outputting here. Testing, I'm sorry. Here I can simply see with one statement that they're testing the transmitter. Okay, is there anything I can do with this one down here? Here we're outputting a character in register A. It's only one statement, so we could, if we were doing a more complex output, we could replace that. But our increment HNL and getting the character is pretty much always stays the same. So let's just assemble this and see how it does. We should have no errors here. Okay, as you can see, we got a bunch of errors here at the bottom, and the reason is I didn't change. We don't have an in macro. We had an in macro for test ready 0, but there is no test ready 0. And we did not have an in macro for test TX ready 0. Let's see what happens now. We still have some errors here, don't we? Do an assembly. Test TX ready. As you can see, I'm still fighting. We didn't put a 0 on this one. All the names are going to have to match. Oh, okay. We're still using a label down here that don't exist. So I need to do something about this. Yeah, we can just take this label, and a macro can have a label at the beginning of it. So it's just like a regular instruction. So now test ready is the label here on the loop. Decrement and jump non-zero test ready. We covered this in the previous demo, how we're looping to output all 12 characters. We loaded 12 characters in here in the B register. So now we can see that, sorry people, I'm not a professional video maker. All right. So now we can see that this should assemble now. Okay, I had to do a little troubleshooting here. If you notice at the bottom on our output pane, build pane, it says symbol TST underscore TX underscore RDY0 cannot be used in an expression. And what it's complaining about here is at the top I made a mistake. In the loop of testing, if the UART becomes ready, I told it to branch back to the label that I have here as the name of the macro. That was a mistake on my part. You cannot use this as both a symbol and as a macro. So as a symbol, it would be, like here, begin app would have the address of where this assembles out of memory, or test ready would have the physical address of this label. But in this case, we have to have another label down here. We're going to have to give us an extra one. So how about we just TX ready 0? Let's just take that code, that label, and we're going to stick that in right here. And we'll correct this to where it reads the same. Excuse me. And then we'll assemble again, and we see we get no errors. I also added this scope statement. So if you notice from the help file of ZDS, we can look up scope. What this is telling us is to make what is inside, what we're using it for in this macro, is to make it local labels. So in other words, what I'm saying is I'm using the label TX underscore ready 0. If down here I was to add jump to TX ready 0, and we had invoked this macro here, and it had included this code in the assembly. It had replaced test TX, it had replaced it with what's inside this macro. If I come down here and try to jump or do something with this label, it won't know what I'm talking about. That's because the scope statement is telling it the labels inside the macro are to remain local. Only inside the macro does it understand this label like it does here. Anywhere outside the macro, it does not see that label, so you could use it again. This way your macros don't, Your macros do not have to know what labels someone is using and worry about someone using the same label or interference, etc., because they're private locally inside the macro. So now if test ready here, we perform this macro, which the assembler is going to fill in with this code, and pretty much the same program that we've had all along, except now when we look at the source code, we can say, oh, well, he's originating at the example demo program location that's been assigned up here. Is jumping to begin the app, so that means here is data, and we begin the app. We set up some registers. We invoke this macro test. So I look at that and I say, oh, I've seen that a million times. It's in all the different programs. Anytime he does this, he's testing to see if the transmitter is ready to receive a character. And if not, it's looping inside here. You can't see the code, but it's looping inside here. When the UART becomes ready, we fall through and output the same as we've been doing and continue to loop around. We can loop right back here using the label that's at the beginning of the line where the macro is at. That's fine. We're going to continue looping until we do. So let's tell the assembler to build and go on that. It's not complaining down here at the bottom about any errors. And what do you know? UART 0, it's outputting hello world. So in this video, we've covered a couple of things. The EQUATE statements, the macro statements. That's something new to us here. Hopefully you already have a good idea of what's going on there. I can tell you, if you ever look at the assembler output of a C compiler or almost any compilers, they have their own macros that's been made for those compilers that the programmers created. And you'll notice that most of the assembler code that's being output from the compiler is heavily macroed. And then that's fed into an assembler and assembled, then linked, so the loader can load it in RAM memory. That works pretty much the same if you're talking to TRS-80, CP/M, or if you're talking a mainframe computer of today. They still pretty much follow the same sequence of events. Doesn't matter if you're compiling Fortran or Python or some other language. You're going to have a compile phase, which is going to generate a pseudocode, and we call it a pseudocode because normally it's heavily macked, full of macros, and this is then assembled, and normally don't call it a source code, but it is a source code to the assembler. Most people call that a pseudocode, the output of the compiler between it and the assembler. So we've covered the EQUATE statements, and we've made a macro, and our boss is happy. He feels that the code looks a whole lot more readable now, and maybe easy to maintain in the future if he tells someone to come in and he wants them to change where it loads in memory, make a new assembly, or someone has to look down here and see what this program is doing. It's a little clearer now. We have a test TX ready 0, and most sites that you have, your IT department, they will have built macros down through the years, maybe decades. I've worked at places where they developed their assembler over decades for an IBM systems, and they have their macros published just like you would for any language. And you go in, and when you're trying to read someone else's assembler code and you run across macros, you can look them up and see what they do. We can also tell the assembler that when you assemble this and you run across this macro, show me in the assembly listing how this is assembled and what that macro is. So the code that it generates here, it will actually output that in the assembly. So let's look real quick at our own assembly code for this particular program. Our demo, here's the list file, .lst, that's in our directory. And we can see here that it assembled. We have 0 errors, 0 warnings. There's 47 lines that was assembled. And here you can see this is the program counter on the left, 3000 hex. That's where we told it to originate. Here you can see our hello world. Here's the bytes right here. Now the test ready, we just show a line number. We don't show any binary data in here. We can tell directly assembler to output everything that it filled in the blank here to list all of that for us. So we'll cover that in a future video, telling it to expand the macros. That's usually called listing or expanding the macros. But we can tell that we started at 3015, and the next program counter that was used was a 1 Bravo. So here 15, 16, 17, 18, 1 Alpha was all used inside this section of code right here, and we picked up with the next memory location. So this code is more readable. If we decide that, for example, the boss comes in one day and says, you know what, we have to add something to this macro or to this testing ready. We need to check and make sure there's not an error with one of the UART registers or something like that. If you were doing, maybe you've wrote a program and you have 100 different places where you're testing ready on UART 0, outputting. Maybe you have 100 different places in this program you've developed that you use this one macro. Or you don't have a macro and you manually typed it in. Well, if they came in and said, you know what, anytime you test that ready, you also need to test and see if there's any framing errors on it. Excuse me. You would have to go back and find all of your 100 different places in the code that you had entered this text, and go in and change every one of them. Well, we solved that by creating a macro. Here we just have a macro statement. It invokes this code. I want to point out, it's important to remember, this is not a subroutine. This code up here is not assembled. It simply replaces this statement. So whatever we used here, 6 bytes or so, that'll, every time we invoke it, it's going to use that same amount of memory. This does not call this routine up here like you might think of as some type of function. However, it simply creates the same routine over and over each time we invoke this label. So if we decide that in here we need to check one of the other registers to see if we're truly ready, or the boss wants to add some other step, we would simply add it here in the macro and add some step here that he wants us to add. And when we recompile, remember we said we have this in 100 different locations in our source code, it'll change it in all of those 100 different locations. We only have to change it in one place here inside our macro. And when we reassemble, it'll change it in every instance of the use of that macro. Okay, so I hope this helped. We'll continue on with another example and try to keep expanding our demo. Many thanks for watching, and I hope to see you back here again soon. Thanks.